So, welcome to this second video in the hydration module. And in this module, this section, we're going to talk about the CSH phase, which, as we've seen in the overview, is the most important hydration product. So, just as a reminder, what we saw in the overview was that when we have the calcium silicate phases hydrating, that's to say C3S and C2S, we form two hydrates. We have calcium hydroxide, has lots of different names, often referred to as Portlandite or as CH. And this forms about 10 to 20% of a hydrated paste. And then we have this phase calcium silicate hydrate, which is written in this nomenclature C-S-H, which is rather complex. But even though it's complex, we have to understand it, and this is making up, as we've seen, more than half of the cement paste. So what we're going to talk about in this video, we're going to talk first of all about the atomic structure and the composition, and then we're going to talk about the mesostructure, and then we're going to talk about the microstructure. Now, the first point I really want to emphasize is that CSH really is a definite phase with a reproducible behavior. When I came into the field more than 30 years ago, people often talked about CSH like it was this complete, random, unknown material. But what we didn't know before, but what has been really clearly established, that it is a phase with a reproducible thermodynamic behavior. And that's what I'm trying to illustrate on these two graphs here. On these two graphs, you see the results of many, many different experiments carried out over the last 80 years or more on examining the CSH. And always, although there's a lot of scatter because of the experimental measurements, always we see that we get the same behavior of CSH. And the other thing that's very important on this slide is we see that we have this variation in the calcium to silicon ratio of the CSH depending on the composition of the solution. So this variation in the calcium silicon ratio of the CSH is shown by the green boxes on these graphs. On the left of the green box, we have the CSH coexisting with silica gel. And on the right of the box, we have the CSH coexisting with Portlandite or calcium hydroxide. And the coexistence with Portlandite is, of course, the situation we are closer to when we're talking about cement paste. Now, what's important here is that people who've tried to produce calcium silicate hydrate in the laboratory, that's to say we often call that synthetic CSH, mixing different solutions together, they really can make calcium CSH with calcium to silicon ratios of 0.7 to about 1.5. However, when we go to cement paste, we can clearly see that in fact we have CSH of much higher calcium to silicon ratio, but in the range of 1.7 to 2. And this is still somewhat of an open question today, why we can get these much higher calcium to silicon ratios. We now think it's really connected to the difficulty of precipitation of calcium hydroxide. For a long time, it's been realized that CSH is related to the natural mineral tobermorite. And tobermorite is so called because it was found on the island of Tobermory, which is located off the coast of Scotland. And this is the crystal structure of tobermorite. It has a calcium to silicon ratio of 0.83. And the main characteristics of this crystal structure are the following. First of all, we have these layers of calcium and oxygen. So this is what you see here. You see the calcium atoms in this kind of turquoise color and the oxygen atoms in red. So this is the layers of calcium oxygen. And in fact, these layers are very similar to the layers you have in calcium hydroxide. It's probably not a coincidence. And then on these layers, what we see is these chains of silicate tetrahedra. So the silicate atoms are at the center of those blue tetrahedra, and at the corners of these tetrahedra we have oxygen atoms. And this tetrahedral organization of silicon is very, very common in nature. It's what you have in quartz, it's what you have in glass. So, it's really how silica prefers to be. But in this tobermorite, what you see is we form these long chains, and these chains have a repeating pattern of 3. So repeating pattern of 3, we use the word Dreiketten, which in German means 3 chain, and you see we have 2 atoms which are attached to this calcium oxygen layer, and then we have 1 tetrahedra which is sticking out from that layer. And then the third element of this tobermorite structure is what we call the interlayer. That's this region in here, and this region in here contains water molecules and also can contain calcium ions, for example. And in more complex cases, there are other ions, such as alkali ions, which can come into this space. So this is the structure of tobermorite. We know this structure with a very high degree of confidence because we can make single crystals of tobermorite and examine them by X-ray diffraction. So the question then is, how do we go from this tobermorite structure to the structure of CSH? And the main problem here is, of course, we see here we have a calcium silicon ratio of 0.83, but we know that in the CSH we have in cement paste, the calcium silicon ratio is generally much higher than that. In paste, it can be up to 2. So what people have really looked at is the ways in which we can change the calcium to silicon ratio. And I'm going to try and illustrate that in the following slides. Now, the first and most simple way of varying the calcium silicon ratio is to omit these bridging tetrahedra. So we see these bridging tetrahedra here. If these are omitted, so for example here you see this one is missing, then we start to change the calcium silicon ratio. We have less silicon, the same amount of calcium, and as we go through this sequence, you can see on the right here that it's telling you the calcium to silicon ratio, and you see it's going up. So that's the first way we can introduce defects which increase the calcium to silicon ratio. But this is nowhere near enough to take us to the kind of calcium silicon ratios we know we have in cement paste. We need other mechanisms. And the second mechanism we can have is that instead of these hydroxide ions terminating here, we can replace these 2 hydrogens here with a calcium atom. So calcium is a doubly charged ion, hydroxide is a singly charged, so we can go from 2 hydroxide ions to 1 calcium ion. And this then, because now we have more calcium, same amount of silicon, again, the calcium to silicon ratio is increased. And here we see by replacing all the hydroxides with calcium, we can get quite a significant increase in the calcium silicon ratio. But what we see here with this version is that even though we've now omitted all the bridging sites and we've got calcium replacing the hydroxide, this is still not enough to get us to the calcium silicon ratios we see in CSH. So the next mechanism is to work on this interlayer and, to have calcium ions in this interlayer. So here we see various different versions with calcium in the interlayer, and now we're starting to really approach the calcium silicon ratios we find. So this example here is a calcium silicon ratio of 1.5, which is round about the upper limit we find for CSH precipitated from solution in the laboratory. So just to summarize here, what we've seen is that there are 3 kinds of defects we can put in tobermorite. We can have missing bridging tetrahedra, we can have calcium replacing terminating hydroxides, and we can have calcium in the interlayer. And really what's important is that there's no unique way to get a specific calcium-silicon ratio. We can have different combinations of these three kind of defect mechanisms. And what we think is that this structure, the structure probably has a really random organization of these defects. This could be one reason for the low crystallinity, the fact that we generally don't see CSH by X-ray diffraction. Also, the entropic effects of having this random organization of different defects could probably be an important element in stabilizing the CSH structure. So here we show just some examples of a full unit cells of different calcium-silicon ratios. Here we see this one here, calcium-silicon 1.4. Here we see calcium-silicon 1.72. And here we see calcium-silicon 1.94. So this is right now coming to the upper limit. You see that we have most of the bridging sites disappeared. We have mostly calcium ions terminating the tetrahedra, and we have some calcium in the interlayer. The other aspect which is important to talk about is the presence of aluminium. So when we make microanalysis in the SEM, this is what is shown on the left here, then we can quite clearly see that this cloud of points here, which corresponds to the CSH, this cloud of points has a displacement along the aluminium to calcium axis. So we can see that the intersection of these lines from yttrium and monosulfate is coming at an aluminium to calcium ratio of about 0.05. And this corresponds to an aluminium to silicon ratio of roughly 0.1, which is to say about 1 in 10 of the silicon atoms are replaced by aluminium. Other studies have shown that the aluminium tends to be located in these bridging sites, that's to say the tetrahedral positions which are facing out, and not in the tetrahedral positions which are attached to the calcium oxide sheets. And this ratio of about 1 to 10, which we find in Portland cement paste, can go quite substantially higher when we have supplementary cementitious materials which contain a lot of aluminium, such as, for example, metakaolin. Now I hope you have a fairly good idea of the atomic structure and composition, and now we're going to look at the mesostructure. And this area of mesostructure is probably the area where we have still quite a few open questions and need to advance our understanding. So why do we think that CSH has a particular mesostructure? Well, the experimental evidence for this goes back quite a long way. First and foremost is the observation that we have no long-range order. That's to say, in calcium, in normal cement paste, we don't see specific peaks from the calcium hydroxide by X-ray diffraction. The second thing, which was pointed out already by Powers back in the 1940s, was that CSH has this intrinsic porosity. Okay, so what do I mean by intrinsic porosity? What I mean is that when you form the CSH, at the same amount, as you increase the amount of CSH that's formed, you increase the amount of this particular type of porosity. And this particular type of porosity is often referred to as gel pores. And now, in the last 20 or so years, we've had a lot of evidence from different scattering experiments, from neutron scattering, from small angle X-ray scattering, and most recently from proton NMR, which indicates that this gel porosity has a characteristic size of about 4 to 5 nanometers. And if we look at the kind of spectra we have from proton NMR, then we can see this specific peak. Okay, so really there are two schools of thought about the structure of CSH. So on the left here, we see the very widely cited model that originated with Jennings. And Jennings did a lot of work around this idea that you have this colloidal model of CSH. So what do we mean by this colloidal model? We mean in this colloidal model, the little areas of CSH are discrete nanoparticles which are not linked together. And these discrete nanoparticles are made up of about four or five layers of the CSH. On the right here, what we see is what's often called the Feldman-Sereda model, although not all aspects that we're going to talk about here were explained like that by Feldman and Sereda. And this Feldman-Sereda model, we have nanocrystalline regions where the layers of CSH are quite well aligned, and then those layers extend from one nanocrystalline region to another crystalline region. And this kind of arrangement of the layers leaves pockets where we have higher amounts of porosity, which we could relate to the gel porosity. Okay, so this model on the left is somewhat similar to what you have in semicrystalline polymers, for those of you who have made studies in polymers. And now we have to say, well, what's the evidence for one or the other of these models? Well, for me, seeing is always believing, and I think the best evidence is really coming from transmission electron microscopy. So these show you two transmission electron micrographs from cement paste. At this very fine level, people are often distinguishing two types of morphology. The morphology we see on the left here with these kind of fibrils of CSH, and the morphology we see on the right, which is said to be kind of like foils. But in neither of these cases, even though we're at quite high resolution here of 200 microns, in neither of these cases do we really see any evidence for these colloidal particles. Of course, we don't see the CSH layers either. So we don't yet have a full understanding of how this kind of microstructural model at this level might relate to this Feldman and Sereda model either. But nevertheless, my personal feeling is that we have much more similarity, much more chance that the real structure of CSH at that level is something like what we see in the Feldman-Sereda model than it is in the colloidal model. But at the end of the day, I think it's more important to focus on the similarities between these two schools of thought in contrast to the differences. So I've tried to show those similarities here, that, this is the colloidal model on the left, where we have these nanocrystalline regions which are not connected. This is the kind of alternative model on the right, where we have nanocrystalline regions which are connected. And, from many points of view, it's probably not so important which one is correct. In terms of mechanical behavior, for example, we would expect to have quite high forces between these colloidal particles, which would be of the same order as breaking a few sheets as on the left. So that's probably what we can say at this point in time for the mesostructure of CSH. So finally, in this short video, we're going to look at the microstructure. Here we now, I think, have a very clear picture, and our very clear picture really shows us that we have two microstructurally distinct forms of CSH. So this picture at the top on the left here, this is what is often shown. This is this kind of needle-like sea urchin morphology, and this is the kind of CSH that forms early on in the hydration process. It's the kind of CSH that nucleates on the surface of the cement grains, and that's why we call this CSH outer product or early CSH. And then we're quite clear that at later times, we get this CSH, this much more dense CSH, which we can see in this bottom micrograph on the left. We can see this is the outer CSH here, and underneath it's this more dense CSH. and it's more clear to see these two different forms in a cross-section such as shown on the right, which is then imaged with backscattered electron images, backscattered electrons. So here we see an unhydrated cement grain. You can see this dense, thick layer of inner product. It's called inner product because it's formed in place of the cement grain, and just on the surface of that you can see this fine outer early product. Now, those of you who have looked in the literature somewhat may also have noticed that there are these terms high density and low density. Of course, from a simplistic point of view, we can say that the inner product is clearly high density, and certainly in the initial stages, the outer product is low density, but there's still quite a bit of debate as to whether we can make a direct analogy between high density and low density and inner product and outer product. Okay, so that's still something under discussion, but these two different forms are quite clear. So if we now come to look at an overall microstructure of a typical cement paste, we can clearly identify the original cement grains. So for example, here we have a cement grain, here we have an original cement grain, and in this paste the hydration is quite advanced. So we have some regions of unhydrated cement paste, such as here, and these are surrounded by quite dense regions of the inner CSH. And then in the space between these large grains, we can identify this kind of outer CSH. We can see indications of this needle structure that formed very early in the beginning. So to summarize all that, what we've seen today, we've looked at the atomic level structure. This is now really very well understood through contributions that have been made from silicon NMR. We've seen that this is based on these sheets of calcium oxygen with mainly dimers of silica tetrahedra attached. And then we also may have aluminium substitution for silicon in the bridging site. The mesostructure, we still have some open questions. We have either nanocrystallites or nanocrystalline regions with a characteristic size of somewhere in the region of 5 microns. And finally, in the microstructure, we can clearly identify, first of all, what we call outer product, which forms early through solution, and then the inner product, which forms at later times. So I hope that's given you some insight into the CSH hydrates. In the next video, we'll look at the aluminate hydrates. Thank you.